started in, there's conflicting info, because in part of the stuff that was published, it said class goes to 7:30, and in part of it said 7. I was gonna go to 7:30 if that's okay with you guys. Okay, we'll plan for that then. I guess we'll start with talking about a couple of things on the quiz that I didn't get to last week, and a couple of things that there were that I probably didn't do a good job of explaining, but you might have noticed that sometimes you just gotta have a little fun too with answers like flux capacitor. And anybody know what a flux capacitor is? Well, shucks, you gotta watch the Back to the Future movie, man. It falls in the same category of fictional nonsense as a Canuter valve and a chemoflutchy drive unit. But something that I don't think they did maybe a good job of explaining, I found a video here that I think might help. This is from a company that does jet skis, and they are talking about the differences between 4 strokes and 2 strokes, but when we're talking about a stroke, that's the engine moving, well, for example, a downstroke would be from the top of its, farthest top of its travel to the bottom of its travel. That's 1 stroke. Well, that takes half of a crankshaft revolution. But so as you can see right here, we've got the piston connected to this throw of the crank, and when it does this, that's half of a revolution of the crank, and then the stroke going from bottom to top is another half. So there's 2 strokes of the piston during 1 revolution of the crankshaft. And we're going to talk about crankshafts more tonight, but as far as crankshafts go, something I like to talk about is bicycle. If you think about your bicycle, and you've got where your pedals are, and the pedal for your right foot and the pedal for your left foot, those are connected by a crankshaft. And these crankshafts and these engines are same kind of an idea, and we're just connecting more than 2 pedals. But if you think about when your right foot goes from the top of when the pedal's on top to where it's on the bottom, and then back up, that's 1 revolution of a shaft, but you did 1 downstroke and 1 upstroke, so a total of 2 strokes there with that right foot. Does that make sense? Well, let's watch a couple of these quick little videos that might help fill in some of the gaps that I maybe left. So,
a 4-stroke engine takes 4 piston movements to complete its engine cycle. The piston lowers for the intake stroke, drawing in the air and fuel mixture, raises for the compression stroke. The air-fuel mixture is ignited for the power stroke, forcing the piston down. And finally, raised for the exhaust stroke, forcing the exhaust out of the engine.
Okay, so we had how many strokes there?
4.
Right. And how many revolutions of the crankshaft?
2.
Right. And so, like we talked about, we get all the power from that power stroke, and the only way the engine keeps moving is that we've got it rotating and we've got enough mass. So that crankshaft has some mass, but we also put a flywheel on there. I guess on this engine, like this piece here, is part of that flywheel. So it's got rotating mass, and it helps run the piston through the other 3 strokes. But we'll watch that one more quick time, and then you guys tell me if there's any.
For example, a 4-stroke engine takes 4 piston movements to complete its engine cycle. The piston lowers for the intake stroke, drawing in the air and fuel mixture. Raises for the compression stroke. The air-fuel mixture is ignited for the power stroke, forcing the piston down. And finally, raised for the exhaust stroke, forcing the exhaust out of the engine. The cycle then repeats over and over, turning the crankshaft, which is connected to the impeller, which drives the craft forward.
So, so this piece here that we're pushing up and down, it's the piston, right? Now this crankshaft we talked about, now why do you think there's this big chunk here on the opposite side from where we're connecting to it? Any guesses? What do you think, Joe?
Looks like smooth, so it rotates.
Yeah, it's smooth is part of the deal. What'd you say, Rick?
Well, it's probably just added, just like a flywheel, it counterbalances.
Balance is a big part of why it's there. Now, it does add mass, but it is part of the balancing. Now, what I brought tonight, and I guess what I had planned to do tonight is talk about a lot of this stuff for maybe the first third to half of the class. And then during the last half of the class, we've got this Toyota 4-cylinder engine that me and the boys took to the machine shop. We just got it back from the machine shop and it's ready to assemble. And I thought we could assemble some of those components and you can see how they all go together during the last half of the class. And this is the crankshaft for it. And these pieces here are what we're talking about. And if you'll notice, there's some little divots in them. Well, at the factory, when they're balancing these, so that, and what they're wanting to do, so we've got, right here's where we've got a connecting rod that connects to it, and a piston. Well, there's a portion of that mass that also, you know, moves with this throw of the crank. And they have some pretty sophisticated formulas and stuff that they take into account part of the weight of that connecting rod and the weight of this part of the crankshaft, and they want to balance it using this. And if they get that balancing all right, it reduces a lot of stress on the bearings, because there's not sideways force. It reduces a lot of the vibration so that the engine runs smoother. And the more perfectly balanced it is, the higher the RPMs it can run without tearing itself apart. Because one that's poorly balanced will have a lot of vibration, and if you speed that vibration up too much, it will tear itself apart. Does that make sense a little bit? So in this crankshaft, you'll see that there's, on a lot of these throws, they've basically taken a drill bit and removed some metal in places where they determined it needed it for it to be well balanced. So that's how they're balancing it. And these are called counterweights, is what that part of the crankshaft is called. So there's another little bit of this video I thought, let's go over here to 345.
Inherently clean burning from the emission standpoint have significantly higher fuel efficiency. There isn't any oil in the cap. That's one less thing to worry about. And they're quiet, which helps keep it happy.
Oh, let me let that run.
There are two notable drawbacks. Wait, by about 15 minutes. First rows are much more involved to be cleared out. Internally swarm water.
So, like I said, this from a jet ski company, but they're talking about the pros and cons between whether you buy your jet ski with a 4-stroke engine or whether you buy it with a 2-stroke engine. Was going to play their little part about the 2-stroke engines. Before I do that, any other comments or questions about the 4-stroke? Back here to
accomplish its complete cycle in just 2 strokes. It is power stroke. Ignited air fuel charge forces down until it reaches an opening inside of the cylinder called the exhaust port. As the piston continues, it pressurizes the air and fuel mixture to the piston that was drawn into the crankcase during the previous compression stroke. A transport is exposed, allowing the pressurized air and fuel into the cylinder. Finally, the crankshaft continues to turn. The piston rises, closing off the intake and exhaust ports, compressing air fuel charge inside the cylinder. The rising piston also sucks in next air fuel charge under the crankcase from the carburetors. Compressed charge is ignited by the spark.
Here's that reed valve we were looking at.
The biggest advantages are lightweight and simplicity of parts. The engine itself weighs typically less than a 4-stroke power output. There are anywhere from 30 moving parts in a 2-stroke engine compared to a 4-stroke. Also much easier to drive a 2-stroke on the water. Biggest disadvantages are increased fuel consumption, elevated hydrocarbon emissions from its exhaust compared to a 4-stroke. Because the 2-stroke has its intake and exhaust open at the same time, some of the fresh air fuel charge passes through the cylinder and out the exhaust port without ever being burned. Because of this and other factors, 2-stroke engines have higher unburned hydrocarbon output in their exhaust than comparable 4-strokes. There are significant exceptions to this, particularly with engines that use direct injection.
So, that's probably the last I had to really say about 2-strokes, unless you guys want more, but any other questions about the differences between 2-strokes and 4-strokes? Okay. So one of the other things that it seems like folks get confused about a little bit is strokes versus cylinders. But I think you guys pretty much have that under control. But just wanted to talk about it just a minute. So this is a how many cylinder engine? Single. But it's a how many stroke engine? Right. So it's a 4-stroke engine, but it's a single cylinder. And for some reason, it seems like that can be confusing. So this Toyota engine, y'all might not can see that well, but how many cylinders does it have? Right. Now it also happens to be a 4-stroke, but the strokes are, we're talking about something very different from the cylinder count. Now while we're talking about cylinders, you can see that this is a really, one of the reasons I picked this is it's a really good example of a modern automotive engine in the way it's constructed, because the cylinders are cast right into the block. That's not true with all engines. Shucks, some dude didn't shut his ringer off again. Gonna have to fire that guy, aren't we? You know, especially in some air-cooled engines, the cylinders are actually a separate piece that bolts the block. But in all the automotive engines that I'm thinking of that are currently produced or been produced in the last couple of decades, all those cylinders are cast right into the block as part of its casting. And you know, the block by definition is really the foundation that we build the engine around. It's kind of the framework. If you think about your house, the studs that you nail everything to, well, the block is kind of the framework that we build everything around. And if you get a chance, you know, look at that engine out there. We've cut some pieces out of the side of the block, and you can actually see how the water circulates between the cylinders. And that's kind of interesting, because these, as you can see here, there's water circulating there between the outer wall of the block and the cylinder. But I guess one of the things that was on the agenda for last week that we didn't quite get to was a little discussion about the block. But like I said, the block is basically the structure that, and one of the main key things that the block does, you can see it a little better there, but it's where we anchor our crankshaft to. As you can see, why the machining of that bore that the crankshaft goes in is got to be pretty precision if we want it to stay together very long. The block also contains, in all the modern automotive engines that we're primarily talking about here, the block also does a couple of other things. There's drilled passages through it. That's how we get all the lubricating oil where we want it to go. Because as I'm sure you're aware of, why anything's rubbing together without lube don't last too long. So like this shows here, most all these engines are going to have an oil pan on the bottom. We're going to have a strainer that'll strain out any big chunks. And this tube from the strainer to the pump, and there's a variety of ways they run pumps, but from the strainer to the pump, that part of it's under suction. And if there's any breaks in that, we can suck air in and not suck in the oil we want from that strainer. But we're going to suck the oil in, we're going to run it through a filter to catch any of the debris, and a lot of what we're going to catch in that filter is going to be little particles of carbon that make it past the rings down into the pan. But anyways, after it goes through the filter, we're going to pump it through passages in that block, and we can look at where some of those passages are, and I got some of them painted out there, but we're going to go up to all the bearings on the camshaft, all the bearings on the crankshaft, and we're also going to go up and push oil up on top to the cam, rocker arms, all the valve train components. So block design is kind of an interesting thing, and if you look at some of the places where that's cut away, you can see it's pretty amazing how they get those cast with everything we want in that piece of cast iron. A lot of the oil passages will be partially cast and partially drilled. You can see, for example, in this, there's an oil passage that goes the entire length of the block right here that's drilled, and after they drilled it, then the ends of it, and then see it's drilled this way too, they plug the ends of it, but there's a lot of places there that can trap debris too. So when you're overhauling one, it's a good idea to think about places in there where debris can get trapped and try and get it all cleaned out. Because if you've got, metal shavings that are hung up right in here, and you put new bearings in this, and then that metal shaving comes loose and gets down into your brand new bearing, it'll kind of wreck that brand new bearing. So just something to think about there. The other thing that our blocks do is help us cool them. Now you can see these engines here that have these fins. Those fins are for dissipating the heat, and these are air-cooled engines. But since the Volkswagen Beetle, there haven't been a lot of air-cooled engines used in automotive, and air-cooled engines are there again typically used where lightweight is an issue, and we're wanting to keep them light. And there's enough possible complications with that that they're just not used much in trucks, tractors, or automotive. So what we do is try and transfer that heat that we've created in those cylinders into water, and then flow the water up to a radiator, and a radiator has tubes of water going like this and air passages going like this, and we'll transfer the heat out of the water into the air at the radiator. But the other advantage of the water-cooled engines is they cool much more evenly, because that water is all the way around the cylinder, and like we were looking at last night, we're circulating it through the head over the top of that combustion chamber too, and so we can cool it more evenly. In many cases, these air-cooled engines, they'll have some kind of a fan. You can see these blades here are part of the fan on this one that try and help blow air past it, and they'll have some shrouding to try and direct the air, but it's pretty common for them to have a lot higher temperatures on one side than the other side. And there again, that isn't a problem for short periods of time, but something you want to last really well. If you can cool it more evenly, you're going to have it last better. So we'll talk about this a little more in a later class, but as far as the block goes, just wanted you to realize that the water comes into it from the bottom radiator hose. Because what happens when we add heat to a fluid, it tends to want to flow up, right? Same as we add heat to air, what's it do? It rises, yeah. So there's some natural convection flow, but and why would you want to work against that? You might as well work with it, right? So your bottom radiator hose will always be the water going into the engine. We're going to circulate it around all those cylinders. We're going to let it flow up, and as you can see in both of these blocks we have here, the water comes in the front, it circulates around all the cylinders, and then it comes up through these passages into the head, and it circulates over all the combustion chambers, and then we push it out the front. The lower radiator hose is typically connected to the water pump, and so the water pump pushes that water back through the block. It flows upwards. The fact that it's being pushed from behind, it'll flow forwards in the head, and here's where we have a flow control device called the thermostat, and it'll come out and into the top of the radiator. But there again, in the radiator, the cooler water is going to be at the bottom, so that's where we pull it back into the block. But there's a lot of things going on in these blocks. It's got to be the framework, and then we're flowing oil and flowing cooling water through them. And so I guess there's a lot of opportunities for failures, right? One other thing that was on the quiz last week that we didn't quite get to, let me see if I can push the right button here. There we go. Maybe. Well, close enough. It says there should be a yes button on here, huh? So when we were talking about our hydrocarbons, all being, different formulations of, like C14 and H20 is one of the popular ones. All our hydrocarbons, there's a lot of what goes on with them that's all the same.
But they all have different characteristics too. And so depending on which fuel we're using, different compression ratios work better as far as that compression stroke where we're compressing all the air and fuel. So even within gasoline, different types of gasoline require different compression ratios to run really well. So wanted to talk about compression ratio. For example, your typical, 85 octane gas, it's typically going to run really well somewhere in that 7 to 1 ratio or up to as high as 9 to 1 ratio. And I want to talk about those compression ratios, but what we would call avgas, aviation gasoline, which is typically somewhere in that just over 100, we'll just say 102 octane. It will run at those ratios, but it can run up to 10 to 1 real well. But with gasoline type stuff, those are the compression ratios that they work well at. There are problems if we get too low or too high. A different hydrocarbon, diesel fuel, most diesel engines are going to run somewhere between 16 to 1 and 19 to 1. So the compression ratio, what it is, if we've got this cylinder here and our piston is at the bottom. So it's all the way, I'm going to put BDC for bottom dead center. It's at the very bottom. What's the volume of this space? So for example, we'll just pull a number out of the air and we'll say that all of that space is, we'll just say 8 pints. And the units don't really matter for this as long as you're using the same. It could be 8 pints or 8 milliliters or 8 liters or whatever. But it's the ratio that's what we're looking at. So then when this cylinder's here and that piston's all the way at the top of its stroke, what's the volume in here? Well, if that now is 1 pint of space inside the combustion chamber on top of the piston, there's our 8 to 1 ratio. So it's talking about how much we're compressing that air and air-fuel mixture. Does that make sense? Now, one other thing to think about is when we're compressing that, like we talked about last week, we're taking this much air that's 20% oxygen and compressing it, so we're condensing our oxygen or raising the concentration level of it. But we're concentrating everything else in there too, including the heat energy. So raising compressing from 8 to 1 will raise that temperature of that air because we're taking the heat energy that was in this much space and putting that same amount of heat energy in this much space. At that ratio, I don't know off the top of my head exactly what it will raise it to, but there's one that I do know. There's an engine that I work with a lot, which is actually that one right outside the door. It runs 18 to 1. And at 18 to 1, so if you were looking, when so this is the cylinder head for that Toyota. And you can see here where our valves are, there's there's a chamber there, that's where we're having our combustion. And it's between that and the top of this piston is where we're having that combustion. Well, you can see there's a pretty decent area in this engine, but in that one out there, if you noticed, it's a fairly flat top piston and it's a fairly flat head, and they come where they're just all but kissing each other. There's just not much space left in there. But at 18:1 compression ratio, the common temperature at, and this is actually at 800 RPMs, because the faster you do it, the more that changes too. It's right at 1,000 degrees. I don't know why they put a dollar symbol there. That's not what we're after, is it? Degrees Fahrenheit. That's in Fahrenheit. Well, diesel fuel combusts. In other words, starts that flame travel at around 600 degrees. So that's why in the diesel engines, what's done is we'll run this piston up to here. We've created a lot of pressure and a lot of heat, and then we squirt the fuel in through an injector that's sitting right in here, and it actually combusts as it's coming out the nozzle of the injector. In a gasoline engine, that hydrocarbon works enough differently that we can't do that. It just doesn't work. So instead, we'll have a spark plug here that sparks and creates our ignition source. Now, one thing that some folks get confused about is this compression we've talked about and displacement, which is a very different thing, but it is a little bit using some of this, well, it's using the same parts, but displacement. And really the only thing the displacement gives us an idea is kind of how big this engine might be. So anybody know, an engine size, something you've heard of, that this is the size of this engine? There you go, a 350. So what a 350 is, the displacement of that engine is 350 cubic inches. Now, that displacement doesn't tell us anything about the compression ratio, but what the displacement is, we take the area of the cylinder times how far that piston moves times how many cylinders we have. So it's given us an idea how big the engine is. It's really not telling us, there again, okay, you can have a 350 that's running 7:1 compression and running a small cam and makes 185 horsepower, or you can have a 350 that's running 10:1 compression and a big camshaft and making 400 horsepower. So it's not as valuable of information as a lot of people like to think it is, but it does give you a little bit of an idea how big the engine is. Are we talking about an engine with one of these? That engine, if I remember right, the displacement of this single cylinder engine with that piston it's under half of a liter, but I don't remember exactly. It's, matter of fact, I think it's less than a quarter of a liter. This engine here, this 4-cylinder Toyota, it's 2.4 liters. That one in the hall is 5.9 liters. So it gives you a little bit of an idea how big it is. but it does not give you the same information as the compression ratio. They're two different things. Does that make sense? So the displacement is the bore area. Let me put a space in there. Times the stroke length times the number of cylinders. So we'll do one of those real quick. So area, anybody remember how you figure out area? That would be volume. That would be 3 dimensions, and area is just 2 dimensions. Length times, well, and we're working with a circle here. This bore is a circle. So that you're right, we're talking about pi r squared, that's right. So let's just assume we have an engine that has a 4-inch bore, and it has a 5-inch stroke, and it's got 6 cylinders. So pi r squared, well, r is radius, which is half of the diameter, but that's 2. You square it, you're back to 4, right? Well, we'll round that off. 4 times, what's pi, Caleb? Yeah. So we're going to be rough and dirty with the numbers, and we're going to say that pi r squared is going to wind up being somewhere around 12.5. We're going to take that times our 5-inch stroke. So our 5-inch stroke times that gets us to around 62.5. Am I mentally doing the math half right, fellas? Okay, then we got 6 cylinders. So what's that get us? Is somebody running their calculator on their phone, or what's that, Joe? I think it's a little more than that, because 62.5 times 6, well, if it was just 60, we'd be 360. So what are we looking at? About 370 something? Okay. And that's in cubic inches. Now in the English system, we look at cubic inches. In metric, it's typically referred to in liters. But for example, I just happen to know this 350 cubic inches happens to be about 5.7 liters. But all that number's doing is giving us a little bit of an idea how big the engine is. Any other questions on that? Okay, times 61. That gets you real close. Okay, cool. So I guess the next thing I had was to talk a little bit more about the crankshaft. So there again, the crankshaft, we talked a little bit about, what these are for balance, but it's where our connecting rod hooks to, and it's what is used to take that linear motion of our piston and turn it into rotational motion. So just like in our bicycle, we're more or less moving our legs straight up and down, similar to our piston. That crankshaft is turning into rotational motion that we're using to rotate the tires, right? Another thing that is done here in the crankshaft, what do you think all these holes are here for, Joe? Good guess. And typically we want to, in our engines, keep the oil and the water and the coolant, or the, what did you say, oil? Yeah, oil, water, and coolant separated. And these, so there's bearings here. These connecting rods hook here with these bearings, and there again, like we talked, anywhere we got motion, we need to lubricate it, right? So in our block, there's actually going to be oil passages that push oil into the crankshaft through our main bearings, and then it will go through drilled passages and come out through the hole here to lubricate our rod bearings. There's, okay, on some of these engines, they won't have that. On some of these smaller engines, they'll just have a little finger down here that kind of hooks some oil out of the bottom of the pan and hopes they splash it in about the right place. But on all our automotive engines, we want to make sure we get all that oil to the right place because we want that engine to last a long time. So there again, we're going to push it. Now, you hear people talking about oil pressure. Well, basically what the oil pressure is we're guessing, well, I shouldn't say guessing. The engineers have this pretty well figured out. They started out guessing and they've really fine-tuned it. But anyways, the clearance between this rod bearing and this crankshaft is going to be about 0.02 of an inch, and we need that full of oil. But of course, as we're using it, that oil is going to fall out the sides, right? So we need to keep pumping more in there. But when that bearing gets wore out, where instead of 0.02 of an inch of clearance between this and this, we've got 0.07 of an inch, it's going to flow a lot more oil, isn't it? And when you get to that point, in many cases, your oil pump has trouble keeping up. It can't push enough oil to keep up with all of it we're losing out the sides of this. So you wind up having low oil pressure. There's other things that can cause it, but that's the main thing that tends to cause low oil pressure is if the clearances that started out nice and tight have been worn to the point that they're real loose. So talking about that, why past this is a connecting rod bearing out of one of those 5.9 liter Cummins, and you can see how it's worn through 2 of the layers and into the 3rd layer. So you can see how, can I borrow it back just a second, Joe? This shinier layer that you see here is what we started out running against. And then there's a darker gray layer under that. And then underneath that, there's the copper layer. So this one's worn enough that the clearance probably isn't 0.02 of an inch anymore, do you think? So we talked about the piston moving up and down and the crankshaft, but we need to connect those two, right? So that's why we call that a connecting rod. So I've got one here that I've put on the piston. And you can see that this needs to swing back and forth because we want that piston to go straight up and down in its bore and have pretty tight clearances between this piston skirt and the cylinder walls. So that piston's going to go straight up and down, but we're using it to turn a crankshaft, so we're turning this linear motion into rotational motion. So as part of doing that, that connecting rod swings like this, right? So this pin that we have here connecting the piston to the connecting rod, anybody know the name of that? Yeah. Where'd they come up with that name? I don't know. I guess you're right, but anyways, and you will have two basic different designs of those. This one is known as a floating wrist pin because it floats in there. Some engine designs, that wrist pin will actually press in. In a lot of them, it's pressing into the connecting rod and will not move in the connecting rod, the motions between the wrist pin and the piston. Some of them do it the other way. They'll press it into the piston so there's no movement there, and it'll move here. Oh, here we go. We got one unwrapped. This is now this is a brand new piston we're wanting to put in this engine. So do your best not to bounce it off the concrete, but feel free to pass that around and look at it a little bit. And you can see that wrist pin in these float. So like you can see, a floating wrist pin will need to be retained by some kind of a clip or a snap ring. Because if it floats out the side and is dragging on the cylinder wall while we're going up and down, not going to do good things to our cylinder wall, is it? I've only seen that once, but it is a possible failure. You know, in some engines it does, including this one. Well, no, this one's, it's not pushing. I guess it's squirting. Which there are some that will have drilled rods, but this style of system is much more common. So what you've got here is when that hole in the crankshaft lines up with this hole in the bearing, it's going to squirt a little bit out that hole right there, which is going to hit in the bottom of that piston and basically splatter everywhere. We've got a little funnel in the top of this connecting rod right here that catches a certain amount of that oil and gets it down into the wrist pin. And that system is by far the most common. Forced oiling to the wrist pin just doesn't seem to be that common. And you can see these connecting rods have a bushing in there, which is replaceable. So if it's worn on this end, instead of scrapping the connecting rod, you can put a new bushing in it. Interestingly enough, compare those two just a little bit, fellas. So now those bores are a little bit different. So because this is running a little bit bigger bore, why that compensates some for why that connecting rod's got to be so massive. But what have we talked about the last few minutes that might affect that more? What do you think would make it where we require, instead of a 1 pound connecting rod, a 6 pound connecting rod? What's that, Colin? Not so much. Like I said, the displacement is a little different because I think that's a 4-inch bore and I think that's a 3 1/4 inch bore. So that's part of it. But what else would make us need a much more substantial connecting rod? Exactly. The compression ratio. So this is out of an engine that's running 8-to-1 compression. That's out of an engine running 18-to-1 compression. So there's significantly, and like you said, there's a lot more power. But typically, you know, that compression ratio is it did. Oh, so this is out of this, yeah. So that's a 2.4 liter gasoline Toyota engine, which is, you know, used in a Toyota pickup, just a little Toyota pickup. So I think, let me check real quick, but I think that kind of covers what I had to talk about tonight. Unless there's any more questions, you guys want to put this one together and see how some of that goes? I don't. So, fellas, what Rich is asking about is there are some engines built where this cylinder is made oversized, and then there's a sleeve that goes in it, so that when that sleeve becomes worn, you just take it out and replace the sleeve. That's pretty common in semi-truck engines, for example, and big heavy equipment. A lot of tractors will be built that way. It is not. No. With Cummins, typically, and this, as far as I know, is true, 7 liters is their dividing line. Everything they build that's over 7 liters has replaceable sleeves. Everything they build under 7 liters does not. That was their old rule, and I can't think of any exception to that. Now, since we're talking about sleeves, there is another kind of sleeve. There's what's known as a repair sleeve. So these cylinders are these cylinders are just the cast iron that the block is cast from, and then they're machined to a specific size, and they get them exactly perpendicular to the crankshaft. But when they're worn, the way that wear is serviced, where's that little piston at? Is it still, there we go. So look at the marking on the top of that piston, Pat. What do you see there? 50? Yeah. So this piston is machined, is made 0.5 millimeter larger in diameter than the original one. So what's done in a lot of cases is the machine shop will enlarge this cylinder to a bigger size. And in many cases, the engine parts aftermarket, and in some cases, the manufacturer themselves, for example, that Cummins engine out there, they make pistons in 0.5 millimeter over, in 1 millimeter over, and then the block is not considered junk until there's a defect in the cylinder wall that's more than 2 millimeters over size. And what they do at 2 millimeters is they'll bore that cylinder 2 millimeters over, then there's a repair sleeve that presses in it, and then it gets bored back to the original size, and you put an original size piston back in it. But that repair sleeve is not normally used unless the wear or the damage is pretty extreme. And what Rich was talking about to start with is there are a lot of engine designs where that cylinder is manufactured as a sleeve that's pressed in it to begin with. And in many cases, it's not a tight press fit. It's something you can almost push in with your hands. And then a little bit of a puller will suck a worn one out. And in those designs, typically when you buy a new piston, you're buying it with a sleeve. So you're buying a piston and sleeve set because you're going to replace them both together. And I'm not sure why, other than it does require more machining. Because of course, on this, they're machining the block to size and they're done. On a replaceable sleeve design, they got to machine the block to size, then they got to machine the outside of the sleeve to size and the inside of the sleeve to size. So there's more machining there, and I would guess that's maybe why we don't see that in automotive engines. Mm-hmm. Right. Right. Sure. Uh-huh. Right. And that's always a possible complication, and a lot of times we saw that in a lot of the older engine designs, and I don't know why, but it's not something we've seen a lot in, I'm going to say, stuff built in the last 2 decades. And you know, different engine designs, that was more of a problem with than others. And I know there's some engine designs that, boy, you'd start seeing some of that by the time you got to 30 thousandths over, and there were others you could go to 60 thousandths over and not have that problem. But on a lot of engines, why 60 thousandths is typically the maximum that they make any oversized parts for. But there's a lot of engine designs that don't even go that far, and maybe that problem is why. You know, they really are. Yeah, and I really think the cleaner burning is a big part of that. And you know, okay, back in, we'll say, the late 80s, that's when I first started doing a lot of mechanicking. The engines that were being built at that time, you know, lasted better than the ones out of the 70s, say. And the big thing we saw different, there wasn't a lot of metallurgy different at that time. You know, the stuff built in the 70s and the stuff built in the mid to late 80s, there wasn't a lot of metallurgy change. There wasn't a lot of engine design change. But what we did see a lot of change in was the fuel management. You know, in the late 80s, we got fuel injection where, okay, there was a computer that took into account barometric pressure and temperatures, and, you know, there's half a dozen sensors, and calculated the fuel, and we just didn't have near as much carbon. And, you know, that carbon getting down between these rings and piston skirts and the cylinder walls is where we saw a lot of wear. And getting that fuel mixture more correct, so we were making less carbon, really seemed to make a lot of difference in how long they lasted. Now, since then, we've also seen a lot of advancements in metallurgy and how they alloy the materials, and I think that's added to it as well.